Now, it turns out that the superposition principle will let us streamline the method of undetermined coefficients. I'll show this by an example. So find a particular solution to y double prime minus y equals 8t e to the power t plus 2e to the power t. Now, in order to find a particular solution, the method of undetermined coefficients lets us solve y double prime minus y equals 8t e to the power t, and it lets us solve y double prime minus y equals 2e to the power t. So basically, how we would tackle this is as follows. We want to find yp1 of t that solves y double prime minus y equals 8t e to the power t, and then we also want to find yp2 of t that solves y double prime minus y equals 2e to the power t, and then we can find the particular solution to this differential equation. Yp of t is then yp1 of t plus yp2 of t using the superposition principle. So let's take a look at yp1. We wanted to solve this differential equation. And the first thing that we have to do is we have to look at the auxiliary equation to see if we have any extra factors of t in our particular solution. So let's do that quickly here. So we take a look at this differential equation that leads to the auxiliary equation r squared minus 1 equals 0, and that leads to r equals plus or minus 1. That's the solution to that auxiliary equation. And so we know that the general solution then will look something like y of t. So we can actually look at the homogeneous solution. Let's erase this. So yh of t is then c1 e to the power t plus c2 e to the power negative t. Right? There's a 1 here and there's a negative 1 here. Now, what we see is that normally if we would try to find our particular solution, it would involve e to the power t. But since that is already a solution to the homogeneous solution, to the homogeneous differential equation, we have to introduce that extra factor of t. So let's take a look at yp1, and we're going to compare that with the right-hand side. Remember, is c times t to the power m e to the power rt. Compare that. We don't worry about c, but we do see that m equals 1, and we see that r equals 1, and that is a root of the auxiliary equation. It's a root of multiplicity 1. So our general equation for yp looks as follows. yp1 of t equals polynomial of degree 1. So that's a1t plus a naught times e to the power t. And then because we have a root of the auxiliary equation, we have to multiply this by t to the power 1. So that's our particular solution for the first differential equation here. And now let's compare this with the second part. Well, that's c t to the power m e to the power rt. And since there's no power of t here, that means that m equals 0 and r equals 1. And so our particular solution for the second equation is yp2 of t equals, and now we have t to the power 1, because this is a simple root of the auxiliary equation. And then we see that it looks very similar, but now we have a general polynomial of degree 0, and that's just a constant a naught e to the power t. And I want to combine these two, but this a naught is typically not equal to that a naught. So let me just put a little asterisk there. And let's do a double asterisk here. And now let's see what yp of t is when we add those two. So yp1 of t is equal to t times a1 asterisk t plus a naught asterisk times e to the power t, and then plus the second particular solution, that's t times a naught double asterisk times e to the power t. And now we can combine these two. And so we'll get that this is t times, and then it's a1 asterisk t plus a naught asterisk plus a naught double asterisk times e to the power t. Now, we see that this is another constant, and so let's simplify that a little bit. And we get that this is t times, and let's just call this a1t plus a naught e to the power t. So I'll just call this a1, and I'll call this a naught. So now let's see what we did there. We had our differential equation here, and the right-hand side, let me rewrite that. Note that I can rewrite the right-hand side as 8t plus 2 times e to the power t. And so we can actually bypass these two separate steps if we look at it as follows. We have a polynomial in t of degree 1 e to the power t. So what is our particular solution is a polynomial of degree 1, just like we have here, and we introduce an extra t just as before because the root of the auxiliary equation is equal to the r equals 1 that we got from this. So instead of typically comparing the right hand side with c times a power of t, we can now change that into compare. So now instead we compare our right hand side 8t plus 2 times e to the power t. We're going to compare that with instead of c times t to the power m, we're going to write pm of t e to the power rt. And then p sub m of t is a polynomial in t. Now, to find that particular solution, we now still have quite a bit of work to do. So let's write our particular solution. It's given by this. Let's rewrite that. And then we'll have to take a look at some derivatives. So we're going to look at yp of t is, I'm going to write this as a1t squared plus a naught times t, all of that times e to the power t. And then I want to take a look at yp prime of t, and that's a product rule. And I'm going to let you check my work here. So the product rule will then tell us that the derivative of this is, if you combine all the terms, a1 t squared plus 2 times a1 plus a naught, and then t plus a naught, and all of that times e to the power t. And yp double prime of t is, again, we have to use the product rule, and I strongly urge you to stop the video and see if you can do this yourself. But eventually, when you do that and simplify your answer, you get that yp double prime is a1 t squared plus, and then we have 4a1 plus a naught times t plus, and then 2a1 plus 2a naught, and all of that times e to the power t. Okay, now this, when we, the particular solution, when we plug it in here, it has to equal the right-hand side here. So let's see what yp double prime of t minus yp of t is, right? That's this differential equation. So this should equal 8t e to the power t plus 2e to the power t. So we start with yp double prime, and that is equal to, let's write it out, a1 t squared e to the power t plus 4a1 plus a naught t plus, sorry, and there's an e to the power t there. I'm going to just distribute that e to the power t, and then plus 2a1 plus 2a naught e to the power t. And then I'm subtracting yp of t, and so that is minus a1 t squared plus, and let me also distribute that e to the power t. So I have e to the power t here plus a naught t e to the power t, and that has to equal 8t e to the power t plus 2e to the power t. So now what we notice here is that this term with the t squared and the t squared here, that cancels out. And then let's take a look at the t e to the power t term. So there's one here, right? That's the a naught. And then we have this right here. Now notice this is a minus, so this a naught cancels out. And what we're left with is, oops. Let's see. What we're left with now is 4a1 t e to the power t, and then we're just left with this e to the power t, right? So this is plus 2a1 plus 2a naught e to the power t, and we're comparing that with 8t e to the power t plus 2e to the power t. Now let's bring that to the other side, and so we subtract 8t e to the power t, and what we get here is 4a1 minus 8 times t e to the power t, and then plus what we have here is 2a1 plus 2a naught and then we subtract that 2 there, so minus 2 e to the power t equals 0. Now, because this has to equal 0 for all values of t, it means that this coefficient has to be 0 and this coefficient has to be 0. So what we get from there, let's move up here. We get that 4a1 minus 8 equals 0. And then we have 2a1 plus 2a naught minus 2 equals 0. The first one leads to a1 equaling 2. And then once you plug that into the second equation, you see that a naught equals -1. So that means that our final answer for our particular solution here looks as follows: yp of t equals a1, which is 2, times t squared, and then plus a1, but that is -1, so we have minus, and then t times e to the power t. And that's our final answer for the particular solution to this differential equation. So this allows us to revisit the method of undetermined coefficients. Remember previously we had to compare the right-hand side of a differential equation with a power of t times a constant times e to the power rt. But with the superposition principle, we saw that we could generalize that into a polynomial of t. So here we have a polynomial of t times e to the power t. Then you can have your particular solution be a polynomial of the same degree times e to the power t with an extra factor of t, depending on whether or not r is a root to the auxiliary equation. So this is summarized here. To find a particular solution to the differential equation ay double prime plus by prime plus cy equals a polynomial of degree m times e to the power rt, we then use the form yp of t equals t to the power s times a general polynomial of degree m in t times e to the power rt. If r is not a root of the associated auxiliary equation, we take s to be equal to 0. And if r is a simple root of the associated auxiliary equation, we take s to be equal to 1. If r is a double root of the associated auxiliary equation, we take s to be equal to 2. We can also generalize finding particular solutions if the right-hand side involves cosine or sine. So to find a particular solution to the differential equation ay double prime plus by prime plus cy equals pm of t times e to the power alpha t cosine beta t plus qn of t times e to the power alpha t sine beta t, where beta is not equal to 0 and p sub m of t is a polynomial of degree m and q sub n of t is a polynomial of degree n, then we use the form yp of t equals t to the power s times a general polynomial of degree k times e to the power alpha t cosine beta t plus t to the power s times another general polynomial of degree k times e to the power alpha t sine beta t, where k is the larger of m and n. So you have a degree m here, degree n here, you let k be the max of those two. If alpha plus I beta is not a root of the associated auxiliary equation, we take s to be 0. And if alpha plus I beta is a root of the associated auxiliary equation, we take s to be equal to 1.